Last time we closed our lesson, we were talking about the summary on limits, and one of the important things that we touched when we were dealing with this, we said that if you are actually evaluating a limit as x approaches some value c, either this value is a finite number or infinite or negative infinity of some function h of x, and you find out that when you're plugging this c in this function, you are getting a 0 over 0, or you are getting an infinite over infinity. Then you can apply what we call you have this thing here, you have an h here, you have an o here, you have a little head there, and then we have L'Hopital's rule. We apply what we call L'Hopital's rule, and of course this L'Hopital's rule, because in most cases we are struggling with our computers or with most of the devices we're using to actually end up adding that little head there. So we usually say that this is Hospital's rule. So we usually write this instead, but the real name for this is this one, so that when you're getting this in a certain textbook or you're getting that, you must know that this one is the correct one, but this one here is the one that we usually use, but we mean the same thing here. But the name is still saying L'Hopital's rule. And now, if it happens that you are actually, when you're plugging this c inside, you are getting other indeterminate form like 0 raised to 0, or you have infinity raised to 0, or you are actually having let's say you are having infinite minus infinity, or you are getting 1 raised to infinity, all you need to do, you need to convert this function, rewrite it in such a way that this is converted to that when you're plugging in a c. And we dealt with this nicely, we dealt with that nicely, we dealt with those nicely. The only issue that we were actually having here is the fact that, and also there was also 0 times infinity, and we also dealt with that nicely. The issue we had was around this, and I did give some advices on how to deal with this. Bear in mind that when you're getting infinity minus infinity, it means that you are having your h of x is equal to some function f of x, such that if you are plugging in here, you are getting infinity minus some function g of x, so that when you're plugging in here, you are actually getting this infinity there. And I said that some people usually just generalize this and say this is actually the same. They factorize f of x and say, I'm going to factorize f of x, or force the factorization, and f of x divided by f of x is just a 1, and then minus, and then we're actually having g of x divided by some f of x, and then after that they say, okay, this is just the same as 1 minus g of x divided by some f of x, and then they divide this whole thing by 1 over some f of x. So what is basically happening here is this one here is kind of converting the denominator. So we're actually having a denominator here, and this one is actually saying we are having an infinity in the denominator of the denominator. So if we're plugging this infinity here, you will get 1 over infinity, and then this one is actually going to be a 0. So we are actually achieving a 0 somehow, but here we are having a problem here because we are having an infinity over infinity, and this is actually giving us a problem. So don't do this factorization. I know what I'm saying, even though there is no maths that you broke, but you're not gonna achieve the goal of actually evaluating that limit. And also another thing that I said is this, if let's say you wanted to change this, another way some people usually advise, and some of the textbook, I think the 5 textbooks that are in front of me are actually saying this. They are saying that you can actually convert this and say that you are actually going to end up having some f of x times g of x. So I am forcing a factorization of this and factorizing and end up getting that, and then inside here what will actually happen is this. I'm gonna say f of x divided by this whole thing, and then I will end up having some g of x minus, and then when I'm dividing that, I will get 1 over f of x. So when you're having this nice thing here, you will actually realize that this is actually going to end up becoming a nice thing of 1 over g of x minus 1 over f of x, and then you divide this whole thing by 1 over f of x times g of x. So if you are having this infinity minus infinity, most of our textbook are saying you must try and do this. Guess what? Because this function here we have h of x is equal to f of x and minus g of x, you will find out that this one is actually going to infinity as x approaches that constant, and this one is also going to infinity. And now when you look into this, once I have 1 over g of x is going, this one is actually going to end up going to 1 over infinity, and then minus, and then this one is also going to be 1 over infinity because our f of x is going to infinity. And then here we'll end up having 1 over infinity times infinity, and infinity times infinity, we know that it is the same as infinity. And then of course 1 over infinity, we know that 1 over infinity is just a 0, and then 1 over infinity, we know that it is a 0. 0 minus 0, we know that it is a 0, and then 1 over infinity is a 0. So we have actually converted that function to actually belong in this particular group here. That is why we usually say this one is actually one of the right ways of actually converting this function and actually end up using L'Hopital's rule in this function, because what is actually going to happen here, you will end up having g of x all raised to minus 1 minus f of x, and then this one is actually raised to minus 1 and all over f of x times g of x, and then this whole thing raised to minus 1. Of course, this is usually good in theory because you can see that I'm trying to actually use some algebra to actually deduce this. And if you are following this nice thing here, you will find out that you might end up getting something in a long run. But of course, I'm always saying that run away from doing these things and do just simple factorization. Don't do this thing. That's what I'm actually saying to you. It is actually working, but please try and not do it and just do easy factorization. Let me give you an example of what I'm actually saying here so that we can actually get to the important topic of the day. Suppose I'm saying to you, evaluate the limit as x goes to infinity of x cubed minus x. So if you are looking into this, we have two functions here, and then if I'm plugging here, I will end up having infinity minus infinity, which is what I'm talking about. But if you look into this, the easiest way is to just realize that I can actually factorize the right way here and just take the x out, and then I will be left. If I take 1x, I will have x squared minus 1, and then if I continue to factorize here, I will end up having x, and then this one is a perfect square, so I'll have x plus 1 and x minus a 1. So we have that, and now if you are plugging in now, I will end up getting infinity and infinity plus 1 and infinity minus 1. And of course, I still have this infinity plus 1. I mean, infinity is so big, so infinity plus 1 is still going to give you infinity. And then infinity minus 1 is so insignificant. Even if this was a million, infinity is assumed to be the biggest number that we'll never touch. So minusing a 1, we're still going to get the same thing there. Infinity times infinity, we're taking two biggest numbers and we're multiplying them. We'll end up getting another big number, and then multiply by infinity is just the same as infinity. So this limit, you can see that it is straightforward when you're doing it like this. But now, if you decide to say that this limit as x approaches infinity of x cubed minus x, you want to convert it using the method that we're using, you will end up having something like this, x raised to infinity, and then in the numerator, you'll end up having 1 over x minus 1 over x cubed, and then you divide this whole thing by 1 over x times x cube, and then of course this is going to be the limit as x approaches infinity of this one is going to be x raised to minus 1, and this one is going to be minus x to the minus a 3, and then here you will end up getting this one, there is a 1. When multiplying powers of the same base, you add the exponents, so this is the same as x to the power 4, so we'll end up having x raised to minus a 4. Now my question to you is, when you're using L'Hopital's rule, you will end up having to take the derivative of the numerator and then take the derivative of the denominator. I will give you this and say, try and take these derivatives and see what you are actually going to get, and see if you can actually end up evaluating this limit or not. But one thing that I will tell you is that this thing that is happening here, that you are ending up getting infinity minus infinity, is not gonna go away when you're taking these derivatives. That is why I'm saying when it comes to the generalization of this minus that, I usually just say manipulate the function or factorize like this. I am not smoking nyaupe or high or anything. I am trying to give you an advice of you end up wasting your time because of what is working in theory and what is actually not working in some other cases. So that is why I usually say try and factorize the normal way, and then you will be able to actually do what you actually wanted to do. And then we ended up closing our lessons on limit. So we closed it. I just wanted to highlight this thing here that most of us usually do when we are facing easy things like this. Just factorize and then deal with this thing. Now, let's leave the limits alone. I hope you still get something, and I want us to talk about local extrema, maxima, and minima. That is the most important lesson of today. So basically what we'll be talking about here is the absolute maximum, the absolute minimum, and maximum, extremum, minimum, extremum, and local minimum and local maximum. Those are the things that I want you to actually end up getting. So that is local extrema. So that's what I want us to talk about today, which is maxima and minima. So those are the things that I want us to talk about. The first derivative test. So I'm just gonna say the first derivative. This is not like looking nice. The first derivative test. So basically we will look at the first derivative, second derivative, concavity, and then from there we will talk about I want us to talk about the mean value theorem, the extreme value theorem, and Fermat's theorem, and then after that give you some few summary on what you actually need to do when you want to find the interval where the function is increasing or decreasing, or where the function is actually having a concave up or the function is having a concave down. And then after that we will end up closing the lesson, and then in the following lesson we will actually look at the examples that are concerning finding the intervals where the function is increasing and when it is decreasing, concave up, concave down, and we will look at optimization. After optimization, I believe that will just give you the steps of actually plotting a function. Once I give you those steps, this is what you actually do when you want to plot a function. I know that plotting a function is not part of your syllabus, so we're not gonna plot functions, but I'll just give you a guideline. So it's not part of your syllabus. We're not gonna actually plot it, just gonna give you the guidelines and why it is important to know those things. And then after that we close everything that has to do with the derivatives, and we start with integration and integrals. So that's what we'll actually do. Let us start now with the definition. I'll try and summarize as possible, because the more I expand this, the more it looks like there are so many things that you need to know. So I'll try and make sure that I give you a little bit of summary and also some notes. So write these notes down and always reference on them. So the first definition is saying this: let C be a real number. It is a real number in the domain. So we must have a function and its domain. So let's say be a real number in the domain df of a function f. Then if I take this C and plug it inside this function, there are some things that will actually happen. Then I will say then f of C is called, okay, let me use a red here. So here we actually will start with something that is actually called absolute maximum. So the absolute maximum, or a global maximum. If the question is saying find the absolute maximum, or a global maximum, or a maximum extremum, those three things actually mean the same thing: absolute maximum, global maximum, or maximum extremum. So I'm just gonna write this. We have maximum extremum. Okay, what does that thing actually mean? Mathematically, so we have this extremum. We usually say that this one, we usually say it is a value of f on D, right? So this is just the domain. It is a maximum value of f. It is a value of f, right? Such that if I take that value C, this value is always going to be greater than f of x for all values of x. So the meaning of this thing is just saying that if you are talking about the absolute maximum, or a global maximum, or a maximum extremum, it is the highest value this function can have on its domain. It is the largest value this function can have in its domain. That is what an absolute maximum, or a global maximum, or a maximum extremum is actually saying. That's all you need to know. And then when we are talking about, let me write what I'm saying here so that at least you can actually get it. It is the highest or largest value of the function f. So that is what an absolute maximum or a global maximum is. The highest value this function can actually have. And then after that, we actually end up having something called the absolute minimum, or a global minimum. Usually some examiners like this one, others like that one. You have to know them both. Or usually someone say it's a extremum, so you are either using this word or that word or this word. What is this thing? This one, mathematically, we usually say that it is a value. So it is a value of f on the domain. It is a value, maximum value on the domain of this function, such that when I'm taking this value c and I plug it inside this function, this value is always less than all other values of f of x for all x in df. For all x in df. So basically what we are actually saying this is, we usually say that it is the smallest value of f. So it is the smallest or the lowest value of f. That is what an absolute maximum or a global minimum or a maximum extremum is. So that is what I want you to know. There are also another definitions here, because I want you to know these things. So the first one, we usually say, let C be a real number. So it is a real number on df on the domain. So it is on the domain df of a function f, right? So we're actually having that. Then f of c is called, so we're actually having here the local maximum, and then we also end up having the local minimum. So what is the local maximum here? So the local maximum or the local maximum, it is a value. First of all, I want you to notice something here before I can proceed. We are not talking about the x value here. We are talking about the y value. So we are talking about the highest value or the highest y value or the lowest y value. And also here we are talking about the y values. So here it is a value of f, right, on df such that if I take f of c, I take c and then I plug it inside f, this value is always greater than or equal to f of x for all x near c. So basically the absolute maximum, if I plot a graph, it is the highest value there is. But this one here is saying that if I have some value here, whenever I pick a value that is close to it, it must always be less than that value. That is what is actually saying. It doesn't matter if, let's say, when I'm plotting a function, I plot it and then I end up getting something like this, and you can see that it is like this. As long as, if you notice that this value here, when I pick a value that is so close to it, those two values are less than this. So this point here, we usually call it a local maximum. Yes, it is a maximum, but in this local community or in this village here or in this town, it is the max, not in the whole function. But the absolute, it is actually the value that is highest in all the other values, the largest value the function can have. But this one here, it is the largest in this neighborhood. So that's what this thing is actually saying. And then the local minimum is also a value of f on the domain df such that if I take f of c is always less than or equal to f of x for all values x near c. So here we're actually talking about the value that is somewhere there, and then after that any value is always above it. So if I pick a value so close it's above, but it doesn't necessarily mean it is always less than all of them. It might happen that the function is actually gonna go down all the way and go down all the way, and this value is less than that, but we are not talking about, we are only talking about if I were to talk about the neighborhood or literally this community that is around this point, are all these points close to it, above it. So if these points are above it, we usually call this point a local minimum. Unlike the absolute minimum is saying that we want the function to be actually having that point as the lowest value of f that is actually available. So that is actually what these definitions are actually saying. Let me actually give you some plot or examples of functions, and we actually look at the absolute maximum, absolute minimum, and actually the local maximum and the local minimum. So if let's say I have a curve here that is actually looking something of this type. Suppose I have a curve that is looking like this, and then we have a nice vertex here, and then it goes all the way, and then it comes down, and then it's go all the way, and then it goes up. And let's say the function is actually ending up there, and I call this function f. And I wanted to call let's say this one, I move it like that, and then here I have this is point A, and then this point here I'm gonna call it point B. This is not a B. And then I take this point here, I call it point C, and then I call this point here down there the x value is going to be point D, and then I'm gonna call this point here point E. Okay. And then if I look into this point, in order to get the output here, I know that this is going to be f of A. And then if I look into this point here, it's going to be f of B. I'm going to take this B and plug it in this function to get this point. And if I'm looking at this point here is going to be f of C, if you get it here. And then, of course, if I'm looking at this point here, that point here is actually end up gonna be called f of E. And then if I look at that point there, when it actually started to intersect with this function here, we're actually going to end up having f of D. So I want us to take a note into this. Let me wrap this example so that this looks a little bit cleaner. So I am going to use this tool here and say that I want to take this down a little bit, and then so that here I can write a nice example and say this is actually saying I have an example. Okay. Now, what is basically happening here is that if I were to look at this point here, you can see that whenever I am picking a point close to E, and this point here, I'm gonna hit the output here. So this output that is here is always above this point, which is defined. And then if I pick a point on the right of E, and then I go and check its output there, I will find out that the point that is here is always above this point. So this point in this here, if I were to just rewrite this, you will find out that if I place my cycle here or get this neighborhood, all the points that are within this circle are actually above this point. So we usually say this one is going to be a local minimum because it is the lowest value that there is. But if you look at this point here is above this point, and also it is above that point. So this point is not the absolute minimum, so it is only the local minimum. And if you look at this point here, and then I draw a little circle there, all this point that is there around this point, a point that is so close to this point, and a point that is around this point here. Of course, when I was drawing this whole thing, I wanted to look nicely and smooth like this. Yeah. So if you look into this here, a point that is close to this is always less than or equal to that point, and a point that is here is always less than or equal to that point. In other words, this point here is the largest value that I can get in this particular neighborhood. So it is the turning point somehow, because it is max, and everything that is close to it, it is less. So we usually call this one a local maximum. maximum. So this one is actually a local maximum. But if you also look now in this function, this is the highest value this function can actually have. All the other points that are in this particular function are actually less than that point here. Any point that is here is always less than that point. So this point, even though it is a local maximum, it is also an absolute maximum. So I want you to understand that this point is also an absolute maximum, and also it is a local maximum. Of course, absolute maximum means that it is also a global maximum or maximum extrema. So this point, it is both absolute and a local maximum. And then we go to this point here. So if I were to pick this point that is here and its neighborhood, any point that is inside here that is on the left, just on the left of this C here, and you go all the way up, I am going to hit a point that is above this point. And when I'm picking a point so close to C and then I go up to the curve, I will find out that any point that I'm actually picking here is above this point, because I'm actually having something of that type. So any point that is here is above this particular point. So this one is the smallest value or the minimum value in this little interval. So this one, it is the lowest or the minimum. So it is a local minimum. So we have a local minimum here. But this point here, it is still above some point that is here, because you can see that if I look into this point, its output, and then I look at a point that is here, it is below that point. So this one is actually not an absolute minimum. So if I look into this point here, you can see that this point that is here is actually somewhere there, and it is the smallest value this function can actually have. So this one here, because it is the smallest, we call it the absolute. So it is an absolute minimum. So we have an absolute minimum. And now let's talk about this point here. If you look at that point that is there, this point here is actually not an absolute maximum or a global maximum, because it is less than that point. So the only option it can have, it can actually be a local maximum. But if you look into those terms, you will find out that I have this point here. I have this nice point there. Let me use a green. I have this nice point here. But when I start to draw a circle around this point, you will find out that every point that is on the left is actually less than that point, but every point that is on the right, there is no point on the right. So we cannot say, because every point that I pick within that cycle is always less than point, we cannot say that this one is supposed to be a local maximum, because I cannot pick something on the right. So we cannot say that this one is a local maximum. So the end points, we don't usually call them local maximum or local mean. The same thing with this point here. If I were to pick this point and circle it, every time I pick a point on the curve that is close to this point, you will find out that every point is always bigger or equal to that. But when I'm picking a point on the left, you find out that I find nothing. So this one, we cannot say not a local minimum, because there is nothing on the left of it. Here there is nothing on the right of it, so we don't usually say it is a local maximum. And this one is actually more important, because and also if you are in class, you have to actually make sure that you understand from the person who is teaching you that are they considering these points, because most cases some people, they want to argue, but in most of the textbooks that are usually used, the end points are usually not considered as local max. We only check if are they absolute max or absolute mean, and it ends there. So that's how we end up doing this nice thing. I hope you can actually get this, that this point is an absolute minimum, this point is an absolute maximum, and also because it is some kind of a turning point, it is a local maximum. And if you look into this point here, every point close to it is always less than that point. So this point, we also call it a local maximum. Right, so we are having 3 to 4 points. We have f of a, we have f of b, we have f of c, we have f of d, we have f of e, and then we said at f of a we are actually having absolute. So we are actually having an absolute absolute minimum, or absolute absolute minimum, or a global minimum. And then at f of b we are actually having a local maximum. And then at f of c we said that we are actually having a local minimum. And then at f of d we're actually having a local maximum. So we have a local maximum, and also at the same time we're actually, and this is not or, so absolute or that, and we are actually having absolute maximum. So you have the local and you also have that. And most cases when you're answering these questions, make sure that you specify if a point here or this output is both the local maximum and absolute maximum. And when it is not, that's when you just say that it is just local maximum or local minimum. And then at point E, we said that we are only having a local minimum. So what we are actually doing here, when it comes to a local maximum and local minimum, we're actually trying to check some sort of kind of a turning point kind of a thing. And for this one is for max, and then this one when you're having something like this or like that or something like this, but as this point is there, we're actually looking at the local minimum. That's what is important here. Let's take another example here. So I'm just gonna try and get another random example here. So if you look into this function here, so I have a function like this, and then it goes like this, and then it goes like that. At this point here, you can see it is the lowest. So here we have an absolute minimum. So this one is absolute minimum, and at the same time, because this one is actually every point that I pick close to it, they're above it, so it is also a local minimum. And then this one here is only the local maximum. So this one is local maximum because this point over here is way above that point, so the absolute maximum will be here, not here. Here we're only having a local minimum, and of course this local maximum. And of course here we cannot say this is actually a local maximum, because when I'm actually trying to draw a circle, I cannot pick anything here on the left, so it is only the absolute. We cannot say it is a local anything. And also here we cannot have a local anything because when I'm drawing a circle, I can only find something on the left, but on the right I cannot have. But here when I'm drawing, I have something on the right, I have something on the left. Therefore this one is also bigger and this one is also bigger than this point, so it's a local min. Here we're actually having a local max. Another example will be something weird like this. So suppose I have a function here that is growing like this. So it grows and then it hits some point there. We have this here, and then after that I have something that is here, and then it goes all the way down here. So if you look into this here, what will be the absolute minimum? Because if you look into these points, let's say this one is 0, and then this one here I'm gonna call it A, This one I'm going to call it B. So if you look at f of 0, what is f of 0? F of 0 here, because it is an endpoint, when I'm drawing a circle, I cannot find something on the left, so it is not local, anything. So it is not local anything. It's not local maximum or local minimum. We cannot have it because there's nothing on the left. And then if you look at B here, and also this one here, if you look at f of 0. So if I'm plugging 0, I look at this output. This output is bigger than f of B. So this one is bigger than f of B. So f of 0 is not absolute minimum, because there is something that is less than it. So this one is still bigger than that point. And now if you go and look at A here, so if you look at f of A there, you will find out that this point here is defined, and this point here is actually the largest point this function is actually having. If this function is called f, then f of A is actually called the absolute maximum, or you can call it the global maximum. Maximum. So we have a global maximum that is here. And then once you actually have done this part here, you will find out that this whole thing now is actually saying, let's investigate if f of A is also a local maximum, yes or no. And if you look into this point here, we have our A here, and A is actually going there, and here is not defined, but it is defined up there. So if you look at this one, if I were to draw it, I will draw it and stand here, and then I have to jump to draw this. So at A, we have a jump discontinuity. I hope you still remember points of discontinuity, because here we are actually having a jump discontinuity. So we have a jump discontinuity. But does that mean that we're not having a local maximum here? So if I pick a point just on the left of A, I will go all the way and I will hit a value that is somewhere here, which is less than that point there. And if I were to pick a point on the right of A, I will hit a point that is there, and this point here is less than that. So both on the left and both on the right, I am actually hitting something, and all these points are actually less than that point there. So this one here, we also call it the local maximum. So it is a local maximum. So it is both local maximum. And another thing that you can think of, if I were to draw a circle here around this point, what is actually going to happen? Because some people say, but say you talked about drawing a circle or the neighborhood around that point. So the neighborhood on the left is going to cut something that is here, and when we are talking about the right, then the neighborhood is going to cut something that is here. So of course this neighborhood around this point is something of this kind. So everything that is on the right is always lower than that point, and everything that is on the left is always lower than that point. So we are actually having a local maximum in this particular case. But if this point here was not defined, we were not going to have an absolute maximum or a local maximum in this point, because this point is not defined. If I were to define this one here, and that one that is up there is not defined, because we wanted to find the highest value of this particular function. So if we're looking at this point here, you will find out that this point is defined here, but the largest value is close to that point. But there are so many numbers that are so close to this that we cannot specify and say close to this point we have 5 comma something something. We don't know that number that is so close to that point. That is why we usually say that at f of A, we don't have an absolute maximum, or the absolute maximum does not exist if the point that is defined up there, the point that is supposed to be defined there, is not defined, because we cannot really say what is the value that is so close to that, because between, you know that between 1 and 1,01 there are infinitely many numbers in between this number, so I can't really pick the number there. That is why we usually conclude that there is no absolute max or global max there, and also the local will not be there. But if this one is defined like I explained, then you know that it actually exists. So we have talked about local, the absolute maximum, which is the highest value the function can have, and its another name is actually called global maximum, and the another name is usually called maximum extrema. And then we have talked about absolute minimum, and then the absolute minimum or the global minimum is the lowest value or the smallest value the function can actually reach. And then we talked about its other name. We usually say that it is minimum extremum. And then we also talk about local maximum. The local maximum is some sort of a point. That point must be defined, and then secondly, the function must be moving from increase to decrease at that particular point. So, or we can say that it is some sort of a turning point, the highest turning point. And then the local minimum is actually a value whereby the function is actually having in a certain neighborhood the lowest point or some sort of a turning point. Now, I want us to actually talk about the extreme value theorem, and then we'll move from there and start talking about other things, of course.